Hey folks, I'm Mr. Hartzler here for Hartzler University, and I want to talk to you about inverse relations and functions. So let's go look at our target and some vocabulary, then we'll get into some examples. So our target is that you can represent the inverse of a relation using some tables, graphs, and equations. And then our vocabulary is what an inverse function is, right? An inverse function is an inverse relation of a function. And then a relation is just any set of ordered pairs. So we got an x and then a y, where x is independent and y is dependent. And then an inverse relation is where we switch those. So our regular relation is just x's and then y's. And then an inverse relation is where we switch that. So we actually have y's and then x's, or our independent or dependent variable are switched. And then that inverse function is really, more than anything, it's that symbol right there. As long as you understand that definition, that we're switching our x's and our y's, or independent and dependent variables. All right, let's go and look at some examples. All right, so here, over on the left is our relation. On our right, it is our inverse relation. So the only major thing that happened there is my first x used to be a -2. Now my first y is a -2. While my first y used to be a 1, now my first x is a 1. So I'm switching my x's and my y's. That is pretty much it. That's all that happens here, okay? You'll notice all the way down, my x's and my y's just switch, and that is it. Now the question comes up, is my new thing still a function? Because originally it is. Now is it? Well, a lot of people are then like, well, what's a function? Well, if it passes my vertical line test, it's a function. So let's graph all of these just real quick. Doesn't have to be pretty. Just kind of toss it up there. So I have a 1 and a -2. I have a 4 and a -1. A 3 and a 0. A 1 and a 1. And this does not pass the vertical line test because if I drew a line right there, I zigzagged a little bit, but if I drew a line right here, I would cross through 2 points. If I cross through 2 points, not a function, folks. Not a function if I can cross through 2 points. And that's with my vertical line test. Really, if it passes a horizontal line test, that's when it's more of a one-to-one function, which is kind of neat too. But anyway, vertical line test to see if it is still a function. Let's go into our next example. So find an equation of an inverse relation. Here, we actually have it as a function. So let's graph this function real quick. We go up 1, and then we go up 2 over 1, because that's what my slope says, right? That also then means down 2 to the left 1. So I have this line right here. Okay. Now that we have that, let's go try and find our inverse. So if I have some steps over here, right? Number 1, switch the x and the y. There's no y yet, but we all know that f of x is the same thing as y, right? Right. Let's switch my x and y. So now it's x equals 2y plus 1. Now I want to solve for this y. Subtract my 1, subtract my 1. Then I need to divide by my 2. So now y equals x minus 1 all over 2. And I'm just going to leave it like that. But you could have also written it as 1/2 x minus 1/2. That's fine too. But this isn't equal to y anymore. This is actually equal to our inverse function. Originally it was f of x, so now it's f inverse of x, or the inverse of my f function. I show that with that -1. Same thing for this one, even though these are both the same answer, just written slightly differently, right? Those are both the same. Now let's graph that, and the bottom one might actually make it easier to graph. So I cross down a half right here, and then I go up 1 over 2, up 1 over 2. So then it's also like going down 1 over 2. So let us connect those dots. Okay. All right, so what's neat about this is you can see that they're kind of symmetrical, right? Tilt your head a little bit. I guess my camera's reversed. So if I tilt this way, I match up. And it actually should, if I did this right, be a reflection across this line right here. Across the line y equals x. That's where it should be symmetrical. So turn your head, see if that works. It does. Neat. And then just to quickly check, is it a function? Yes. Yes, it is. And that is because I still, if I'm only looking at this line, I do pass the vertical line test still. So that's awesome. Is still a function. Let's keep going, look at some next examples. All right, so here, I'm going to start off by writing an equation for the inverse of f. Okay, so I'm going to find my inverse. Then I'm going to check a bunch of stuff. But let's do a first. I need to find my inverse. First thing is I'm going to set my left y instead of x. Negative 1/2 x plus 5. Now I switch my x's and my y's. So now it's x equals negative 1/2 y plus 5. I subtract my 5 over. So x minus 5 equals a negative 1/2 y. If I multiply by a negative 2, I should get rid of that 1/2 now, right? It should be positive, double negatives. 2 times 1/2 should get me a 1. Cool, so that cancels, but I need to do it on the left. And it's going to need to be distributed, folks. Don't forget that piece. So it's a negative 2x plus 10 equals y, but not my y. That's actually my inverse function. Okay, found it. Now what's it say to do? Okay, so did A. Now B. Use composition to show that f and the equation you wrote are inverses. Okay, to check to see if two things are inverses, I have to do two things. I have to, one, I need to check f inverse composed of f of x. And then I also have to check my f composed of f inverse of x. I have to do it both directions. And it's weird because sometimes it'll work one way and not the other. And then, of course, other times it's switched. And then sometimes it won't work for either. Sometimes it'll work for both. And if it works for both, we're good. It needs to work for both. And what I mean by working is these things should both end up equaling x. If they equal x, we're good. All right, well, let's try it out. Let me do f composed of f inverse first, just for funsies, which means f with my inverse function plugged into it. Okay, so my f function, it said negative 1/2 times my input plus 5. That's what f function says. So now I'm going to plug f inverse into that. My f inverse is negative 2x plus 10. So negative 2x plus 10. All right, so now I need to distribute all this, see what we get. And we get a positive x minus 5 plus 5. That equals x. Sweet, that works. So that one was number 2. We actually did number 2 first. Oh, well. Then we're going to do number 1. So that's f inverse composed of f of x. And then I need to take my f inverse function, and I need to put my f of x through that. So my inverse function says negative 2. Let me draw a little line here. Negative 2 times my input plus 10. That came from right here. All right, so what's my input? Well, f of x. F of x was the original way up there. So negative 1/2 x plus 5. Same thing as last time. I need to distribute that negative 2. I get a positive x minus 10 plus 10. That does, in fact, equal x. Awesome. So number 1 also works. So I've used composition. I compose f inverse of f, and I have f composed of f inverse. So I do it both directions. Make sure both of them work. If one of them does not, then it doesn't work. And now I need to sketch the graphs. Okay, sketch a graph of f and its inverse. F was this initial one. So I go up 5. Oof, I'm going to count by 2s. So I go up 5, down 1, over 2, down 1, over 2. There's that one. Then I need to graph my inverse, which was right over here. Which means I go up 10. Oh, I'm actually going to go off my paper. Darn. And then I go down 2 over 1. 1, 2, 3, 4, 5. Okay, so down 2 over 1. Down 2 over 1. 2, 1, 2, 1. So it's going to be something like that. Terrible drawing, but you get the idea. And then my line right there, you can see if I turn my head, it is symmetrical about that. Sweet. So check that. Ooh. How can you verify by the graph of f and its inverse that they are indeed inverses? Well, that's with symmetry. And that's what we just did there, right? We turned our head a little bit, and it checked out. Cool. Is the inverse of f a function? So that means, does it pass the vertical line test? And yes, it does. If I look at that one, either of those lines on their own pass that test, we are good to go. So I've now done D, and I've done E. Sweet. Let's go on to our next example, folks. All right, so on this one, we need to find the inverse of the function by identifying an appropriate restriction of its domain. So let's start off by graphing the original chunk here. Well, that's a quadratic. I know that much, but I need to try and figure out what it looks like. So f of x, let's see if we can factor this. I think it will. X plus 4 and x plus 4. That's going to be good because that simplifies even further. Because remember, 4 times 4 gets me that 16. 4 plus 4 gets me that 8. So that's how I know it factors like that. So x plus 4 all squared. Well, that just is a quadratic or a parabola shifted to the left 4. So 1, 2, 3, negative 4. So I got to circle there, and it's a parabola. So it looks something like that. Oh, a little hard to see on the screen, but you get the idea. All right. So now I got to find the inverse of that. So let's do that part first, and then we'll look at its domain. So I have that, right, my normal stuff. Just copying it down as is. My first step is to replace my x with my y. Remember, f of x is just y. So that now becomes x, and I have y squared plus 8y plus 16. I need to solve for y. You've done this before lots of times, maybe not millions, but hundreds, sure. So I'm going to factor my right side. And we've already done that, right? I did it up at the top of the page just to kind of see what it would all look like. Now I need to take the square root of both sides. So I have plus or minus, because I took the square root of an x, equals, now it's just a y plus 4, right? My square and my square root cancel each other. So now I need to subtract that 4. Subtract my 4. So plus or minus square root of x minus 4 equals y. But it's not a y anymore, right? That's actually my inverse function. Okay, I don't know what that graph looks like too, right? That's a square root graph shifted down 4. So I'm down 1, 2, 3, 4. Let me change colors, actually. That might help. Shifted down 1, 2, 3, 4. So I'm here, and I look something like that. Okay. But now, if I look at that inverse, that's not a function. If I draw a vertical line there, I cross it most places in 2 spots. That's not good. I can't have a function like that. So we're going to restrict the domain of my original. So if let's cut off part of this. Let's cut off this chunk on the left. Well, we have to remember that inverse functions are reflected across that line there. So that chunk becomes that chunk. So let's look at what this does to my domains in range. So of my original, my domain, right, assuming I still left all of it, is all real numbers. So I'll write negative infinity to infinity. And my range was from 0 up to infinity. But I restricted it now. I cut off that left half of that parabola. So it's no longer this, but instead it is, what is that? Negative 4 to infinity. And now for my inverse, my domain and my range are the same as my original ones, but they're switched. So now my range becomes my domain. So my domain should be 0 to infinity. And my range should be what my old domain is, which is negative 4 to infinity. Let's check out that graph. Again, just that top part, right? Just this chunk here. That's the only part I'm keeping. So, does that match this? My domain, 0 to infinity. Start at 0, and I go to the right. Cool. Range. Start at negative 4, and I go up to infinity. Start at negative 4, I go up to infinity. Sweet, that's it. So, my answer to all of this, right? Identifying an appropriate restriction of its domain. My restriction is that my domain must be -4 to infinity. That will ensure that my inverse stays a function. Okay, because my initial part is a function, but as I rotate it, or as I reflect it to make it an inverse, it does not stay a function anymore. So I have to restrict my original so that my inverse stays a function. Alrighty, let's go on and check out our next example. Alright, sketch the graph of f, then verify that the inverse will be a function and write an equation for that function. So let's graph this. Ooh, it's a cubed function, right? I go up 2 and to the left 1, and I'm reflected. That 2 in the front says I go up 2. Up 2. Then I go left 1, and then I'm reversed. So I typically would have this go up, and then that part go down. But I'm going to be switched this time. So let me erase that, and we'll write the good one. All right, so now instead of going up, I go down first and then up. Okay, normally it goes like this for a cubed root function, but this time I'm not doing that. Instead, I'm going to go down first and then up. I've reflected across my y-axis. Sorry, I've reflected across my x-axis because that negative in front. That's a reflection. Okay. So that's what I look like right now. I need to sketch the graph of f, then verify that the inverse will be a function, and write an equation for my inverse. So if I want to pass my vertical line test to make it a function, well, but that's for my inverse, right? So for this one, if I were to check it, it's a vertical line test. I'm switching on my x's and y's. So if my initial passes a horizontal line test, then the other one should pass a vertical, right? Everything's going to be backwards between these two. So for my inverse, if I need to pass a vertical line test, then for my original, I need to pass a horizontal line test. And does it? It does. Cool. So it probably will. Sweet. All right. Then verify that the inverse will be a function and write an equation for that inverse. Let's write the equation for that inverse. First thing I'm doing is I'm switching out my f of x for my y. And then I'm going to switch my x's and y's and solve for my new y value. Okay. So 2 minus cube root of x plus 1. Let's switch x's and y's. Now I need to solve for y. So I'm going to subtract my 2. Now I need to get rid of that negative out in front. So I'm going to divide by a negative. Means everything on my left switches signs. How do I get rid of that cubed root? Well, I have to raise it to the third power. Then I need to subtract my 1. And I ran out of space. So let's write it up here. This, remember, is my inverse. And it's going to be negative x plus 2 cubed minus 1. Awesome. Let's not worry about graphing this one right now. It actually didn't even ask me to anyway. But this is my function. Since my initial does pass a horizontal line test, then my inverse will pass a vertical line test. All right, let's go on and check out our next example. All right, so use composition to determine whether f and g are inverses. Well, this is where I plug one into the other, and then I have to do it the other way, right? So to verify that they're inverses, I have to go both directions. I have to take f and compose it of g, and I'm also going to have to take g and compose it of f. Well, let's do that then. That means on this one, I'm taking f, and I'm taking my g and putting it in f. Well, what's f say to do? Well, it says 1/4 times my input plus 7. What's my input now? Used to be x. Now it's all of g of x, which is 4x minus 7. So 4x minus 7. All of that gets plugged into my input. Now, what do we get? Distribute that 1/4 gets me x minus 7/4. And I have to add 7. Ooh, I'll tell you right now, folks, negative 7/4 plus 7 does not equal 0. So that means this is not inverses. I don't have to do anything else. Right there, I know my answer. Sweet. But let's just check ourselves. Let's do more work because, you know, we all like that. Let's take our G function and let's plug f of x into it. My G function says 4 times my input minus 7. My new input is all of f of x, which is 1/4 plus 7. 1/4 x plus 7. Distribute that 4 in, I get x plus 28 minus 7 does not equal x, so not inverses. Neither of them work, so we're good. If my second one would have worked, I would check myself again on my left one just to make sure I did everything right. And if I did, then they're still not inverses. As long as either of those don't come out to equal x, not inverses. But it's one of those things, right? If this one does, that one doesn't, I should check the one that doesn't, just to make sure, you know? All right, let's go on and check out our next example. All right, here we are using compositions again. Let's do this. F composed of G. Well, it means I'm taking my F and putting G of x into it. So my G function, my F function, says to take the cubed root of my input minus 1. Well, what's my input? All of G of x, which is this whole thing, x cubed plus 1. Let's simplify first. So cubed root of, well, what's x cubed plus 1 minus 1? Well, that's just x cubed. Well, what's the cubed root of x cubed? Well, x. Sweet. That one works, but we have to check out our other one. So G composed of F is G with f of x plugged into it. My G function says my input cubed plus 1. What's my input? Well, it's my f of x, so it's all of that. Cubed root of x minus 1. Third power, third root, cancel each other out. So I end up with x minus 1 plus 1. Ooh, equals x. Cool. Now since both of them, both of them have to equal x, we are good. So we say yes, inverses. That's all I have for you today, folks. Please, if this video was helpful, hit that like button down below. Subscribe to the channel so you can see more like this, and hit that little bell and you'll get notifications when I post new videos. Have a great day, everybody. Make sure you keep doing your math carefully and with enthusiasm. Bye, folks.